Okay, now that you have seen, first of all, my demonstration of the electric force, my lecture on electric fields, and also my demonstration of the electric field itself. Now that you have watched those videos, we can now ask and answer the following question. Exactly what is the wave nature of light? That is, what is the wave? Okay, well, to answer that question, let me go ahead and redraw one of the electric field diagrams that you saw in my electric fields lecture, specifically the electric field associated with a point charge. I'll just draw a positive point charge, for example. All right, so let's say that here's a positive charge, and then as you saw in the electric fields lecture, you then have the electric field lines radially outwards in 3 dimensions from that charge. Let me go ahead and draw some field lines like so. Okay, and then as I draw these field lines, I'm obeying the rules for drawing those field lines as described in the electric fields lecture. Okay, now let's imagine what happens in the following situation. Let's say that a force is exerted upon that electric charge such that it accelerates in some manner. So now a force is exerted upon the electric charge such that it accelerates. Okay, the easiest situation to examine is what happens if we set the charge into oscillation. So for example, the charge is set into oscillation. So what happens then? Well, at this point, pause this lecture and take a look at the screencast video that I've posted for you, where we take a look at a couple of clips from a specific Mechanical Universe episode where, using some animation, we take a look and see exactly what happens to an electric field when you take the electric charge and set it into oscillation. So take a look at that screencast now. Okay, now that you've seen that screencast, I can now draw the following diagram. All right, so once again, here's my positive charge, and let me go ahead and draw some field lines. Okay, and then as you saw in the screencast, what then propagates through the field is a little ripple, a wave. Specifically, it's an electromagnetic wave. Now, how magnetism is wrapped up in all of this is an extremely long story. I mentioned that in the screencast as well. In that screencast, the Mechanical Universe episode does a really good job of showing the propagation of that wave as a series of alternating, oscillating electric and magnetic fields. Regardless, however, I'm going to draw that very simply in the following way. Yeah, I'm just going to draw 4 field lines here, because if I draw more than that, then the diagram gets kind of crowded. All right, so here's a field line like so, and then let's say that the ripple in the field has not propagated past this point. Okay, here's another one. Here. And here. Like so. Okay, this ripple that is propagating through the field is what is called, once again, an electromagnetic wave. The speed of this electromagnetic wave in a vacuum is always the same thing. It's one of nature's fundamental constants. It's the speed of light, c, 3 times 10 to the 8th meters per second. This discovery was made in the 1860s. That is, the nature of electromagnetic radiation, the speed of the propagation itself, the speed of the wave, is the same as the speed of light, which had been previously measured earlier in that century. So the speed of the propagation is the same in a vacuum. That's the speed of light. C, which is equal to 3 times 10 to the 8th meters per second. Once again, that's one of nature's fundamental constants. Okay, now because the speed of the wave itself, the speed of the propagation is always the same thing, then we could write down the following kinematics expression from our last unit on mechanical waves. Recall that speed is equal to wavelength times frequency, where the left-hand side of the expression is always the same thing in a vacuum. Once again, 3 times 10 to the 8th meters per second. Okay, now the different types of light, if you will, that are produced in this process depends upon the energy and the frequency that is used to produce that light. So for example, let's say that I take the electric charge and I set it into oscillation like so with a relatively low amount of energy and then therefore a low frequency. This is again then going to produce waves of a low frequency and then therefore a long wavelength, such that the product of the two is always the same value. The speed of light c, 3 times 10 to the 8th meters per second. Let's say alternatively, however, that I take the electric charge and I set it into oscillation with a high energy and a high frequency like so. So then therefore if the frequency is large, then therefore the wavelength is small, where once again the product of the two is always the same thing. This then results in overall what is referred to as the electromagnetic spectrum. The electromagnetic spectrum is just a description of the different types of light that are produced depending upon the energy that goes into the production of that light and the frequency. You're typically going to see a diagram or a picture of the electromagnetic spectrum. There's a diagram of the electromagnetic spectrum, for example, in your textbook. Okay, regardless, however, of which way we draw the diagram, the description of the diagram is always the same. Let me go ahead and illustrate here. Okay, now when I draw this, let's say that if I go from right to left, two things increase in this direction. The energy that goes into the production of the light, and then the frequency. And as the frequency increases to the left, this then means from left to right, increasing to the right has to be the wavelength. Like so. And now let me begin with the most energetic form of electromagnetic radiation of all, what are referred to as gamma rays. The amount of energy that is necessary to produce gamma rays is huge. This then results in a really large frequency and then therefore a really small wavelength. The wavelength itself is usually on the order of the size of individual subatomic particles. So then therefore electromagnetic radiation of this form, gamma rays, is typically produced in nuclear reactions. Okay, and then less energetic than that are X-rays. X-rays are naturally produced, for example, when individual electrons are accelerated very quickly to extremely high speeds, or it could also be produced artificially, like when you go to the dentist's office, for example, and get an X-ray, by taking electrons and slamming them into pieces of metal at extremely high speeds. When this happens, X-rays are produced. Okay, and then we kind of get to the more normal types of light that we're familiar with. There's basically 3 types. There's first of all ultraviolet light, visible, that is what we can actually see with our eyes, and infrared. When you're talking about ultraviolet light and invisible light, these 2 types of light are typically produced when individual electrons transition between energy levels within atoms. When you're talking about infrared light, what we sometimes refer to as heat, then basically you're talking about light that is produced by the vibrations of individual atoms and or molecules. Now the visible portion of the spectrum, what we can actually see as the spectrum of colors, for example, the window associated with that spread of colors is actually quite small. It's only a few hundred nanometers wide here on the diagram. There's a very easy mnemonic to remember for the order of the colors themselves. Roy G. Biv. R for red, O for orange, and so on. The Roy G. Biv on this diagram, however, is backwards. It's like so. Roy G. Biv. Like so. R for red, O for orange, Y for yellow, G for green, B for blue, I for indigo, V for violet. Once again, the window itself here, the window of the electromagnetic spectrum that we can actually see, is only a few hundred nanometers wide. Okay, and then after infrared, we have microwave and radio waves. Microwaves and radio waves are most easily produced, for example, by alternating currents in electric circuits. When you're talking about radio waves that are produced naturally in the universe, that usually occurs with very cool objects, like gas clouds, for example, that exist between the stars and the spiral arms of galaxies. So once again, as you go from left to right on this diagram, the amount of energy that's necessary to produce the light decreases, the wavelength increases in this direction, the frequency increases in this direction. But keep in mind that this is all describing essentially the exact same thing. It's describing a ripple that appears here, for example, in the electric field as you take an electric charge and you accelerate it in some manner. Okay, let me go ahead and pause here for part 1 of today's series of lectures. I'll get to part 2 in just a few minutes.